welcome back. Welcome back. Good to see you all again. So, our plan today would be to finish the FFT section. All right, let's start. So today we'll finish the FFT algorithm. In the last class, we started looking at Fourier transform, but we didn't get to the end of it. So let me just review where we were last class. So we started talking about polynomials, and we saw that polynomials have two different representations. One of them is coefficients. Another one is evaluations of the polynomial. Okay? So you have either the coefficients of polynomials or the evaluations, and we noticed that if it's very easy to multiply polynomials if you have their evaluations. So in the representation where we're talking about evaluations, it's really easy to multiply polynomials. But we want a method to go from one representation to another. So in some sense, if we could go from the representation of polynomials as coefficients to the representation of polynomials as evaluations and back, if we could go back and forth between these representations, then we would have a very fast algorithm to multiply polynomials. Okay? So then we started looking at, okay, how do we go from, let's say, coefficient representation to evaluation representation? So that became this concrete problem. So here's a concrete problem we have. So let me just let me just highlight the problem we have. So here it goes. So you're given a polynomial p0 to pd via its coefficients. You're given a polynomial p via its coefficients, and you're given some number of values, alpha 1 through alpha n, where you want to evaluate this polynomial. So, for instance, p of x is our favorite polynomial, let's say 0 plus 1 times x plus 2x squared plus 3x cubed plus 4x to the 4. And you're given 4 points, alpha 1, alpha 2, alpha 3, alpha 4. Let's say these are numbers 5, 6, 7, 8, some set of numbers. And you want to evaluate this polynomial at these 4 points. And we devised a recursive divide and conquer strategy to do this. Okay? How did we do it? Well, we put all the odd degree coefficients into a polynomial p odd. So p odd has only the odd degree coefficients. So essentially you have a vector. Take every alternate coefficient, put them in one vector. Every other alternate coefficient, put them in a different vector. So you get two different polynomials. This is called p odd and p even here. And I claimed that these two polynomials together can recover p via this algebraic identity. P of x is p even x squared plus p odd x squared. Okay? This algebraic identity actually gives us a way to recover p from these two polynomials. Okay? And using this identity, evaluating the polynomial p at alpha 1 through alpha n reduced to evaluating two different polynomials, p odd and p even, at alpha 1 squared, alpha 2 squared, alpha n squared. So if you see this, so evaluating polynomial p reduced to two problems, evaluate p odd and p even. Both these polynomials have half the number of coefficients, so they're half the degree. And the points where you're evaluating them is squares of the original points. Alpha 1 through alpha n, if you have alpha 1 through alpha n, if you have alpha n squared to alpha n squared. Okay? And then, if you evaluated these two polynomials at these 2 points, this set of points, then you can recover the value of the original polynomial p just by plugging it into the original identity. Okay? And so, just to tell you what happened here. So what happened here is you wanted to evaluate P of x at alpha 1 through alpha n. Okay, and that reduced to two different evaluation problems. Evaluate P odd, which is of degree half the degree. Let me just not use the same letter here. Evaluate P odd of z, let me just call it z, at alpha 1 squared to alpha n squared, and evaluate P even of z at alpha 1 squared to alpha n squared. Okay, so we reduced this problem of evaluating a degree d polynomial at n points, to evaluating degree d over 2 polynomials. These are degree d over 2 again at n points. And then we sort of analyzed how this recursive algorithm does. So we wrote down a recurrence for this recursive algorithm. Let me find it. So we wrote down this recurrence relation for recursive algorithm, and I left it as an exercise, but we found that the runtime of this recursive algorithm is n times d, which is as good as a naive algorithm for this problem. Okay, so we want to do something we want to modify this in a way so that we improve its runtime. Okay, so any questions on this entire schema right now? Yes.
So you evaluated the polynomial at 4 points, but technically you wanted to know P would be 5 points, right? For like a general.
Yes. So the question is related to the question of how many points you need in order to know a polynomial exactly. For a degree d point, you need at least d plus 1 points. So to actually be useful, you need n to be at least d plus 1. If you have at least d plus 1 points on a degree d polynomial, then you uniquely identify the polynomial. Otherwise, it's just a set of evaluations. But so that's always going to be an issue we'll have. So we'll always have to take care that our n is more than d plus 1 where d is the degree of the polynomial we are looking at. Okay? Any other question? But right now I'm going to treat these as independent parameters. We'll soon converge and have actual values. Okay? So, all right. So what went wrong in this schema is that we have a divide and conquer algorithm that kind of splits the problem into two subproblems where the degree drops, but the number of points doesn't. Okay? And that's why we got this bad runtime. So we would want a situation where the number of points also drops when you divide the problem. Okay? And this is where we will use the fact that, in a sense, we don't really care about the points of evaluation. In our original problem, we just wanted to represent the polynomial using its graph, right? And using its evaluations. So we had the choice of picking these alpha 1 through alpha n as we please, right? So if you recall, in our original problem, we were talking about two different representations of the polynomial. We could either represent the polynomial using its coefficients, or the value of the polynomial at a bunch of points, p of alpha 1 through p of alpha n. Here, alpha 1 through alpha n is completely left to us. We can choose any choice of alpha 1 through alpha n. In particular, if there's a particular choice of alpha 1 through alpha n that will make this evaluation faster, we should pick that. So that's what we'll try to do now. We'll try to pick these points of evaluation alpha 1 through alpha n so that this divide and conquer strategy actually works and it gives you a fast algorithm. Okay? Okay. Please stop me if you have any questions at any point. Okay, so let's see where we are. All right, so this is our situation now. So you see that the points of evaluation, if you start with trying to evaluate the polynomial at alpha 1 through alpha n, you end up with the problem of evaluating a different polynomial at the squares. Okay? So if you could ensure that the number of different squares is smaller, then the set size goes down. For instance, suppose for some reason, let's say, suppose alpha 2 was equal to negative of alpha 1. Okay? Let's say we pick points so that alpha 2 is equal to negative of alpha 1. Okay, let's say alpha 1, no, for instance, alpha 1 could be 1, alpha 2 could be negative 1. Okay? In this case, if you look at their squares, when you square the two numbers, alpha 1 squared is equal to alpha 2 squared. Right? So, in particular, if you start with the set 1 minus 1, plus 1 and minus 1, okay, and you square both the numbers, you'll end up with just one number, plus 1. That's nice because, right, so if you're alpha 1 through alpha n over here, at the top, let's say this was just two numbers, plus 1 and minus 1. Okay? For just two numbers, then in the subproblems, I just have to evaluate it at the squares of these two numbers, which is just one number, which is plus 1. So you see that the size of the set, the number of points I need to evaluate, dropped by 2. Right? Basically, I want a set such that if I square everything there, I should get fewer numbers. There should be collisions when I square. So what happened here is both plus 1 and minus 1, when you square them, they give you just the same number, 1. So therefore, you got fewer numbers. Okay? So essentially, if you have pairs of numbers which are plus a and minus a, if you square them, you get the same square. So we want to ensure that our set of alpha 1 through alpha n is rich with these pairs, plus and minus a, so that when you square them, you get a smaller set. So that the number of points of evaluation is also dropping by 2. Okay? So let's just try to construct this such a set of alpha 1 through alpha n by sort of by hand. Okay? So let's see how to do this. So, all right. So let's try to do this by repeatedly taking square roots. So I'll start with the number 1. Okay, I'll start with the number 1. Okay? And what I'll do is I'll take its square root. What are its square roots? Well, its square roots are plus 1 and negative 1. Okay? Okay, so I have two numbers now, which are square roots of 1. So going down the square roots, and in particular, if I square, I get the number on top. Right? Plus 1 and negative 1 are square roots of 1, and if I square any of them, I get its parent, 1. Okay? So let's do this again. Let's just take square roots of both the numbers. So again, the square roots of plus 1 are plus 1 and negative 1. Right? Okay, so now I want to take square roots of negative 1. You can do it in complex numbers, but let's just pretend for now that you can take square roots as you wish. So what's the square root of negative 1? I'll just call it square root of negative 1. Okay, this is plus square root of negative 1 and minus square root of negative 1. Okay? Whatever it is, it's some number. All right? So let's do that again. So you can take square roots of these numbers again. So again, the square root of plus 1 would be plus 1 and negative 1. Okay? Square roots of negative 1 would be, again, square root of negative 1 and negative square root of negative 1. Okay? So now I have to write square roots of this. I'm just going to pretend they exist and continue, right? So what's the square root of negative 1? Well, square root of negative 1 is just square root of negative 1, right? Now the other one is square root of minus square root of negative 1. The other one is square root of negative negative 1. And then the other one is minus square root of negative 1. Right? So let's just pretend that you can take square roots as you please. But the most important thing to remember here is, okay, what are the key observations? Well, every number has two square roots, right? Square root A is this plus square root A and negative square root A. So every number A has two square roots. And more importantly, they are negatives of each other, right? If you look at any node in this tree, its sibling, meaning it's the other child of the parent, is a negative of it. So you see, this is plus 1, this is negative 1. This is plus square root negative 1, this is negative square root negative 1. So in every layer, if I look at any given layer, okay, all the numbers here are in pairs. You have A and then negative A, also part of the list. Right? So every number has its negative in the list. Okay? And you see that there is exactly 8 numbers here. 8 numbers in this layer, 4 numbers in this layer, and so on. Okay? And so moreover, if you squaring, by definition, squaring numbers in layer I gives you numbers in layer I minus 1. By definition, squaring something in a layer gives you something in the earlier layer. Right? Okay? So this is nice because this is exactly, looks like what we wanted. If I look at the numbers in the last layer, if I square them, there are 8 of them, but if I square them, I get only 4 numbers. Okay? And this is precisely what we wanted in this algorithm to decrease its complexity. We wanted the fact that if you square the numbers, you should have half as many numbers, right? And that's exactly what we have here. If I square the numbers in any layer, I get half as many numbers. These are precisely the numbers in the previous layer. Okay? So that's really nice. So this is exactly the construction we want. Okay? So let's just give these numbers a name. So for now, these are the 8th roots of 1, 8th roots of unity, right? Because essentially these are the second roots of unity or square roots of unity. Unity is 1, and so the square roots of unity are plus and minus 1. So they are the second roots of unity. If you take a square root of a square root, it's the 4th root, right? So these are the 4th roots of unity. And a square root of a square root of a square root is the 8th root, right? Meaning, if you take any number in the any number in the third layer, pick any number here, let's call it omega. If you square it 3 times, you'll get 1. Meaning, you take omega, square it, omega squared, square it, omega to the 4, square it, omega to the 8. Omega to the 8 will be equal to 1. That means that the 8th roots of unity are precisely the numbers here. These are the numbers such that if you raise them to the power 8, you get back 1. Okay? So then so let's just use these as our alphas in our schema earlier. Okay? So what am I going to do? I'm going to let's plug in alpha 1 through alpha n to be, let's say, the nth roots of unity. Okay? Let's assume n is a power of 2, and we can talk about the nth roots of unity. Okay? Then over here, I would have the squares of nth roots of unity. Right here, I would have squares of nth roots of unity. Right, squares of those numbers. If I set alpha 1 through alpha n as the nth roots of unity, you get squares of those nth roots of unity, which are just the n over 2th roots of unity, or all the numbers in the layer above. These are just the same as n over 2th roots of unity. Okay, so that's what happened here. Okay, so does it make sense? So this is a nice schema now. Really, what we have is somehow not just the degree is decreasing by half, but the number of points is also decreasing by half every time. Okay? Question?
If the points decrease, why is it not the case that the ordering of the even and the odd functions gets messed up when we sort of club them together to get one function?
Okay, so the question was about how does the decrease in the number of points affect our ability to reconstruct P of x from it. But here's something to remember always, which I sort of... so this identity is a key thing that's driving everything. This identity tells us that if I need to know P of x, I just need to know P even of x squared and odd of x squared. So for instance, if I need to know P of 5, 6, 7, 8 here, I just need to know if I can compute, in order to compute P of 5, P of 6, P of 7, P of 8, I need to compute P even of 5 squared, P even of 6 squared, P even of 7 squared, and so on. And similarly, P odd. So this is a very general fact because of this identity. This identity tells us that if you know the value of these P even and P odd at alpha I squared, then you can compute the value of the original polynomial at alpha I. Right? And for any choice of alpha i's. So in particular, what's happening here is you want to compute P at nth roots of unity. You just need to know the value of P even at squares of nth roots of unity and P odd at squares of nth roots of unity. And it turns out that the squares of nth roots of unity is only n over 2 numbers. So you only need to compute P odd at n over 2 numbers and P even at n over 2 numbers. What ends up happening is you'll use the value of each of these evaluations twice in your when you try to reconstruct P using this formula. But that's not, that's, yeah. it's sort of hidden under the code. When you write the code, it will show up. But for, conceptually, this is what's happening. The identity tells you that you need to know P even and P odd at alpha I squared, and that's what we know. Any questions on this? Any more questions? So this is essentially the FFT algorithm now, because now let me just set d plus 1 equal to n. Just for simplicity, you could also do this analysis with different degree and n, but let's just work with the simpler setup. D plus 1 is equal to n. Then what does the recurrence tell you? It tells you that t of n is 2t n over 2 plus order n. Right? If the polynomial p had degree n, then if the original polynomial p had degree n, the two different polynomials have degree n over 2. Right? This polynomial had degree d, let's say. This polynomial would have degree d over 2, and this polynomial will also have degree d over 2. And the nth roots of unity, if you want to evaluate the nth roots of unity, you have to evaluate n over 2th roots of unity. So every parameter of the problem is reducing by a factor half in the two calls, and so you get this recurrence relation, and that gives you a runtime of theta n log n. Okay. Yes, question. Okay, so it's a great question. The question was, in P odd and P even, is it that the number of coefficients is dropping by 2 or the degree is dropping by 2? Actually, the degree itself is dropping by 2. So, and that's because essentially what we are doing is we have this schema by which we say, if you give me a vector of length L, I treat it as a degree L minus 1 polynomial, right? So in this case, if P of x is, let me do an example. So if P of x is 0 plus 1x plus 2x squared plus 3x cubed plus 4x to the 4, then P odd is just obtained by take all the odd degree coefficients and put them in a polynomial. So, for instance, here, 1x would be, you'll get the vector 1, 3, and so that will be 1 plus 3z. And then the P even would just be take all the even degree coefficients, put them in a polynomial. So it would be 0 plus 2z plus 4z squared. Okay, any questions? Yes. Sorry, I couldn't hear you. I still couldn't hear it. Could from what I hear, the question seems to be, can we write this recurrence in terms of D instead of N? Yes, you could write it in terms of D instead of N, and you'd get the same. Essentially, what I'm treating here is, there are two parameters, D and N. You could write the recurrence in both, I guess. But since in all our applications, D will be roughly order N. I just said D plus 1 equal to N. In all our applications, D will be roughly order N. Okay? Yes. Sorry?
How do you know that all your roots are going to be, well, like the roots that you get from p of are going to be different from the roots, the nth over 2 roots of unity that you get from p even.
So the nth roots of unity are playing the role of evaluation points. They tell me where to evaluate this polynomial at. So they sort of are not connected to the polynomial p at all, right? Initially we said, I'll give you a polynomial, and I'll give you a set of points alpha 1 through alpha n, and evaluate them, right? In general, this problem, we had a recursive algorithm that didn't work out so well. So now we are saying, okay, let's just fix a special set of alpha 1 through alpha n where we have a fast algorithm. And the special set of alpha 1 through alpha n are these points, the ones which we got by just recursively taking square roots. Okay? So what I just did is we just found an algorithm to evaluate any polynomial p at these special points very fast. Right? These are special points, not arbitrary like our original example had of alpha 1 through alpha n, which is arbitrary. At these special points, we have a fast algorithm because they have lots of special properties. In particular, if you look at any layer, they appear in pairs which are negations of each other. Moreover, if you square them and go up a layer, you have half as many points. Still, you have pairs which are negations of each other. If you square again, you have half as many points. You still have pairs which are negations of each other, and so on. Right? And that's useful. That's critically used in our algorithm. Any questions on this? Yes. The question is whether the runtime is big theta or big O. It's big theta. Big theta. Plus, it's big O. It's the same. It is actually big theta. Yeah, but you can write. Okay, so let's proceed a little further. Okay, so that's good. So the one thing that I've hid under the rug is I kept taking square roots just as I please here. I said, taking square roots as you please, and every time you take a square root, you get both a positive square root and a negative square root, right? And that's how we construct these numbers. Over real numbers, you can't really take square roots of -1, but if you use complex numbers, you can. All of these square roots exist, and they're numbers that you can work with, right? But this algorithm that I described just works in any field where all of these things make sense. So there are lots of finite fields where you have these square roots, and the same algorithm works over them. But in our case, we'll just use complex numbers, and over complex numbers, we do have these numbers. So square root of -1 makes sense. Square root of negative or square root of -1 also makes sense. All of them are actual numbers, and we can work with them. Okay, so all right. So let me just define Fourier transform, right, as we have defined it. I've been using the word Fourier transform, but I have never defined it. So in order to do that, I need to give these numbers a name. So let me give them a name. So the nth roots of unity are all numbers x, all numbers omega, such that omega to the, or let's just say all solutions to x to the n equal to 1. These are numbers such that if you raise them to the power n, you get 1. These are the nth roots of unity. And over complex numbers or any field, there are exactly n solutions to an equation of degree n. So there are n solutions to these. There are n of these numbers. Let me call them omega 0, omega 1, omega n. Okay? These are I'm just calling them, these are the nth roots of unity. Sorry, I should use omega n minus 1. Sorry. Yeah. Okay? Okay, so I'm trying to push the push just the details of complex number manipulation to as late as possible. So I'll try to work without introducing complex numbers to as late as possible. So for now, these are just n numbers, such that their nth power gives you 1. Okay? And we saw how to get those numbers formally. For instance, just keep taking square roots, you get 8th roots of 1. Right? And 16th roots of 1 are just square roots of these numbers, and so on. Okay. So what is the Fourier transform? So the discrete Fourier transform, I guess, is the following transformation, but let me just write it as an input-output. You're given as input a polynomial of degree n, or degree n minus 1. So coefficients of a polynomial of degree n minus 1. Okay, and the goal or the output is just the evaluations of this polynomial p at the nth roots of unity. Evaluations at the nth roots of unity. Okay, so it's a specific evaluation problem. You're given a polynomial of degree n minus 1, and you need to evaluate it at the nth roots of unity. Okay, these are nth roots of unity are fixed numbers independent of the polynomial, and you want to evaluate it at these points. All right. And what we discovered just now is that there is, or we just saw right now, is that there is a n log n time algorithm for this transformation, for this Fourier transform. And this algorithm that we described is called the fast Fourier transform algorithm. Okay? The algorithm that we just described is called the fast Fourier transform algorithm. Okay? So it's just the original evaluation problem, but with a specific choice of points, evaluation points. Okay? All right? So let me just, so let's see what this evaluation problem corresponds to as in terms of numbers, right? So what do you want to calculate? You're given this set of numbers p0 to pn minus 1, which is this polynomial, which corresponds to the polynomial p of x is summation pi x to the I. Okay? And you want to evaluate it at, you want to compute p of omega 0, p of omega n minus 1. Right? Okay. So these omegas are the nth roots of unity. If you're familiar with them, I think this is an exercise in the homework. If you're familiar with them, it's good. If you're not familiar with them at this point, just think of them as numbers, because they are really numbers which you can add, multiply, divide, everything. They just have two components, but they're literally numbers you can add, multiply, and divide. Okay, so you just have n numbers which you want to substitute into this polynomial, right? So this transformation that we described from P to its evaluations can be described as you can write it down as a matrix. Okay? How does the matrix look? Well, you write down this matrix. So what did I do here? I just wrote what it means for P of omega I to be, what is P of omega I in terms of the coefficients given to us in matrix notation, right? It's just, I'm just rewriting the formula for polynomial evaluation in matrix notation. Okay, so again, let me call this polynomial, this matrix omega, big omega, maybe big omega is a bad notation. Let me call this matrix big V. So what we have is this matrix times this vector gives you the values, right? So any questions on this right now? I know for someone who's not really familiar with matrix notation, this might seem like, okay, where did this come from? But it's really, what I'm really doing, we can check later, is really just writing down the definitions of what matrix multiplication is and what polynomial evaluation is. So if I look at the ith entry here, P of omega I, that's given by taking the ith row here and multiplying with this column. So this is just rewriting the formula. P of omega I is equal to P0 times 1 plus P1 times omega I to the 1 plus P2 times omega I squared, and so on. Okay? Okay, so it's really what the entire, the Fourier transform, you can think of it as you're given a vector P0 to Pn, and you have this matrix V, which we know, it's a fixed matrix. We want to multiply the vector P0 to Pn with this matrix V. Okay? The naive algorithm to multiply a matrix with a vector takes n squared time, where n is the dimension of the matrix. But because this is a special matrix and it has lots of structure, we just discovered an algorithm that can multiply this matrix with the vector in n log n time instead of n squared time. Okay? So the key piece that's sort of missing in our picture is we have discovered how to go from coefficients to values, but we really want to be able to go both ways. For our scheme to work, we should be able to go from coefficients to values and the vice versa. Right? So we need to be able to go from values to coefficients. Meaning, if I give you the right-hand side of this equation, the inverse Fourier transform problem is somebody gives you the right-hand sides, gives you P of omega 0 to P of omega n minus 1, and you need to find the coefficients P0 to Pn minus 1. Okay? So the inverse Fourier transform problem is the following. It's so you're given P of omega 0 to P of omega n minus 1, and your goal is to compute the coefficients P0 to Pn minus 1. Okay? So that's the inverse Fourier transform. That's the inverse map that goes from the value representation to the coefficient representation. We need that. We need an algorithm for this, right? Because in our original scheme, we wanted to go between representations easily. But I described just one algorithm right now. How do we compute the other way around? Well, this matrix vector equation tells you that V times this P0 to Pn minus 1 is equal to P of omega 0 to P of omega n minus 1, right? It tells you that if you want to compute the inverse, what you need to do is to multiply by the inverse of this matrix. Meaning, if I take V inverse times P of omega 0 to P of omega n minus 1, this will give us the P0 to Pn minus 1. Right, that's, if V times a vector gives you another vector, V inverse times the right-hand side gives you the left-hand side. Okay? So, in general, you would have expected that I would have two more lectures where I'll describe you an algorithm about inverse Fourier transform, which is also an n-log n algorithm, hopefully. But it turns out that V inverse looks very similar to V. Okay? It turns out that V inverse looks very similar to V. In particular, if you take V and you replace omega I by 1 over omega I, you get V inverse. So V inverse looks very similar to V. In fact, V inverse is, this is a fact, V inverse is actually, V, you can treat V with omega 1 over omega I in place of omega I, 1 over n times this. Alternately, it's 1 over n times V complex conjugate, if you know what complex conjugate is. So, okay, I'm throwing a lot of things at you, right? Much of it is algebra that you can work out and check, right? You don't need a conceptual understanding of why V inverse is 1 over nV for what we're going to do. Just believe me that V inverse is actually essentially the same as V with 1 omega I replaced by 1 over omega I. Okay? Then, essentially the same algorithm that we had for Fourier transform, replace all the omegas by 1 over omega, you get an algorithm for inverse Fourier transform. Okay? So let me just leave you with a little cartoon, right? I mean, essentially what happened is, right, here's the issue with teaching Fourier transform. Somehow, the algorithm is a very clever jigsaw puzzle. There's complex numbers, there's divide and conquer, there's inverse Fourier transform, right? Lots of things fit in perfectly to give you this algorithm. And what you can do is I can show you a single piece of the jigsaw puzzle and start fitting in other things. It's kind of mysterious why the other things fit in so well, or why the other things fit in at all. And there's really no explanation for them. It would seem like somebody made these puzzles pieces so that they fit in together. Actually, no, these things existed earlier on. And unfortunately, there's no clean way to motivate every piece of the puzzle, how it fit, why it was made that way. Because it wasn't made that way. It wasn't meant to be that inverse Fourier transform would have the same algorithm for Fourier transform. It's just a fortunate accident, right? It's just a fortunate accident that inverse Fourier transform has the same algorithm as Fourier transform. It's just a fortunate accident that you can take square roots and this is allowed in complex numbers. Right? So many things fit together. So it's hard to motivate every piece. But most of the pieces you rely on just some simple algebraic identities. So as long as you take those algebraic identities and on faith, or just check them on paper and pen, the conceptual part of the Fourier transform is in this divide and conquer strategy that we described in the class. Okay? So I'll stop at this and